Yeah, let's go ahead and get started. I know it's 107. We'll show up at 5, whatever. Let me see if I'll the attendance for them. Let's talk about improper integrals. So here's an example. Here's an example. If you've ever seen an improper integral, this is the first one they probably should do. But it's good to see it again so we can talk about it. So the integral from 1 to infinity of 1 over x dx. This is typically the kind of standard first example you usually see. Kind of better, yeah. So the idea is we're trying to ask how much area is under the curve y equal to 1 over x from 1 all the way to infinity. And the idea is we can't just antidifferentiate this and plug in infinity because infinity is not a real number. So what we're going to do is we're going to replace infinity with a letter. To replace infinity, or more generally, replace the problem or the problematic number with a letter, and then take the limit. So we're going to rewrite this as the integral from 1 to b of 1 over x dx. And you can use b or t or z or a. People use different things. I usually use b for an upper and a for a lower. That's pretty standard. Some people use t for upper or lower. If you use z, it's weird. And then we're going to take the limit as b goes to infinity. So just so you can see what we're doing, we're actually taking the integral. Oh, wow, that's a good picture. Of this function from, say, 1 to b. And we're going to calculate that area. So kind of ignoring the limit, but still writing it in every step, we're going to have the limit as b approaches infinity of, well, the integral of 1 over x is the natural log of the absolute value of x from 1 to b. And then we're going to plug in the limits of integration. We're going to get the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. And that's just 0. And so I will point out, before we take the limit, if you look at the area under the curve is the natural log of whatever b is. That's how much area is actually in the curve. So you go like from 1 to e, the area is 1. If you go from 1 to e squared, the area is 2. But if you let b get larger and larger and larger, well, this natural log of b is going to get infinitely large. And so this limit is going to be infinity, which means the integral diverges. So this integral is divergent. Yeah. Welcome. Oh, let me put my picture on here. Okay, then we just talked about how the integral from 1 to infinity of 1 over x is divergent. The general kind of process for any improper integral is you have to replace the things that are problems with letters. The problems are infinity or negative infinity, infinity are always a problem. And then the other thing we have to start looking at, which we'll see in a minute here, is anywhere the function might be undefined, which isn't a problem here, right? 1 over x is totally defined from 1 to infinity, but there are places where it could be undefined. Look at another example. A question?
Really quickly, you might be able to answer this a little bit later in the lecture as well. So there's a mathematical proof showing that when our power at the bottom is greater than 1, it converges and it's less unequal.
Sure, from 1 to infinity, definitely.
Right. And I can see the proof and it makes sense, but is there an intuition as to why that's the case?
Sure, the intuition is that any function where the power is larger than 1, the function gets small fast enough. That's really the intuition, is that this area under 1 over x is infinite as you go all the way out. Whereas if that power is just a little bit larger, the function is getting small fast enough that the area underneath it is finite.
So the criteria is x1 over x, and if it's growing faster, it's getting smaller faster.
Right.
Like this.
Mhm. So as we'll see in this next example, right, if we look at the kind of second classic example, which is the integral from 1 to infinity of 1 over x squared, we can do the same sort of thing. Well, now, right, similar sort of idea. You've got your 1 over x squared looking like this. And again, we're asking, what's the area under that curve doing? Is it finite? Is it getting infinitely large? We want to know. So again, infinity is a problem. So we're going to rewrite this as the limit as b approaches infinity of the integral from 1 to b. And if I'm going to be doing the integration, I might as well start trying to rewrite this. I'm going to write this as x to the minus 2, just because that makes it easier for me to antidifferentiate. We antidifferentiate, we get the limit as b goes to infinity of the integral of x to the negative 2 is x to the negative 1 over negative 1 from 1 to b. I personally don't like negative powers. Like they just are, especially when it's infinity, just is less easy to see. So I would certainly encourage you to rewrite this as the limit as b goes to infinity of negative 1 over x from 1 to b, and then plug in the limits of integration and get the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Or if you like, the limit as b goes to infinity of 1 minus 1 over b. And then as b goes to infinity, this 1 over b is going to get infinitesimally small. It's going to go to 0. So we're going to get 1 minus 0, which is 1. So this integral converges. And typically when an integral converges, we also say what it converges to. So this integral converges to 1. So the area under the curve, as you move further and further, as your upper limit of integration gets further and further to the right, the area is getting closer and closer and closer to 1. Just like a regular limit, right? When you take a limit of something, you're saying the function getting closer to that value. You're not necessarily saying the function ever equals that value, just that it gets really close to it. Questions about this so far? Okay. So, and then I will point out for Manny's kind of observation, if we look at the integral from 1 to infinity of 1 over x to the p, if p is greater than 1, then we can really easily see that this converges. I'm going to write this as the limit as b goes to infinity of the integral from 1 to b. I'm writing this as x to the negative p. And you don't actually need to write this down. I just kind of want to show it to you. You are welcome to write it down, of course, but I just want you to see what happens here. When we integrate this, we get the limit as b goes to infinity of, let's see, x to the negative p plus 1 over negative p plus 1 from 1 to b. And I will point out that since p is larger than 1, that means negative p is less than negative 1, and negative p plus 1 is less than 0. So the negative p plus 1 is negative, or if you prefer, p minus 1 is positive. The reason I point this out is because I'm going to rewrite this. I'm going to write this as the limit as b goes to infinity of 1 over negative p plus 1 times, instead of x to the negative p plus 1, I'm going to write it as 1 over x to the positive p minus 1. And again, observe that power is positive if p is larger than 1. Makes sense, right? If p is larger than 1, p minus 1 is definitely positive. From 1 to b, and then if we do this, we have the limit as b goes to infinity of 1 over negative p plus 1 times 1 over b to the p minus 1 minus 1 over 1. And then since p is since p minus 1 is positive and b is going to infinity, 1 over something infinitely large is going to get infinitesimally small. That's going to go to 0. So you're going to end up with 1 over negative p plus 1 times negative 1, or positive 1 over p minus 1. So if p is larger than 1, this integral converges. I will mention right now, since it's gonna come up next quarter. This is how later on we're gonna show that the series of 1/x or 1/n to the p converges if p is greater than 1. So that does come up later on in 21C, and we talk about the convergence of series and sums, but yeah, we're not there yet, but someone will be like, oh yeah, we'll do the integral test and we'll show this converges, and that's why it converges. But let's look at some more examples. I will also say, if you wanted to on your own, you could show that the integral of 1/x to the p, where p is less than 1, diverges. Yeah.
All the examples that we did in class and all the examples that we're doing now, they all start at 1. Why can't they start at 0?
They can start, so these ones specifically cannot start at 0. That's an excellent question. So if this is started at 0, and this actually goes to where we're going to go shortly. But if I want to look at the integral from 0 to infinity of 1/x squared, the problem, and so this is something you're going to have to take into account now whenever you see a definite integral, is you have to look for where that function that you're integrating might be undefined. And the issue here is that f of x equal to 1/x squared is definitely undefined at x equal to 0. Good rule of thumb, we can only deal with one problem at a time. It's a good life rule, right? Maybe not really. It'd be nice. What I mean by this is this integral from 0 to infinity has two problems. 0 is a problem and infinity is always a problem. So whenever you have two problems, you have to break it up so that we only have one problem in our integral. Meaning I'm going to rewrite this integral from 0 to infinity of 1/x squared as the integral from 0 to, take your pick. Literally any number you want to choose is fine. Most people would choose 1. But really you could choose 6 or e or pi or anything between 0 and infinity. But usually we choose like the next available integer, unless there's a good reason not to. So I'm going to write this as the integral from 0 to 1 of 1/x squared dx plus the integral from 1 to infinity of 1/x squared dx. And I will point out from the work we just did, we know that this piece converges. It adds up to 1. The area under that curve is 1. Let's look at this other piece. So just like you have to replace infinity with a letter because infinity is a problem, in this integral from 0 to 1 of 1/x squared, we have to replace the 0 with a letter. So I'm going to rewrite the integral from 0 to 1 of 1/x squared dx as the limit as, I typically like to use an a for a lower bound. Again, you can make whatever choice you want. As a approaches 0 of the integral from a to 1 of x to the -2 dx. Now, I've actually left off something that's minutely important. Our interval is from 0 to 1. Meaning we are between 0 and 1. Meaning specifically we are bigger than 0. Right? If we're between 0 and 1, we're bigger than 0. Which means that a can't approach 0 from both sides. A has to approach 0 from the right-hand side. So if you're replacing a real number with a letter, you need to be aware of which side you're approaching it from. And basically, if it's a lower limit, you're always approaching it from the right. From the right. If it's upper limit, you're always approaching it from the left. Because if it's an upper limit, we are less than that limit. And if it's a lower limit, we're greater than that. I find it easy just to draw like a little number like, oh yeah, I'm like right there, greater than 0. So I'm approaching it from the right.
So this kind of method also works with functions like tangent of x?
Yes.
It just depends on whatever that asymptote.
Right. So what I would say is, yes, we're always looking for the asymptote, or more generally where the function is undefined, which is typically a vertical asymptote, but not always. So here, if I do this integral, I get the limit as a approaches 0 from the right. Integrating x to the -2, I get x to the -1/x, or as I like to write, -1/x from a to 1. And then I get the limit. And you do need to write the limit in each step, which I know is kind of annoying, but we kind of need to. As a approaches 0 from the right of -1/1 minus -1/a. Or I do like to simplify this. I don't know why. It's probably not at all necessary. I would write this as 1/a minus 1. But then as a goes to 0, 1/a is going to blow up to infinity. So this limit's going to be infinity. Which means this part diverges. And if you add up a divergent thing and a convergent thing, what do we get? Overall divergence. Basically, as soon as one part diverges, the whole thing diverges. So if I was doing this integral, like as a fresh new integral that I hadn't seen before, and I broke it up into these two parts, if I had done this first part and it diverged, I would stop. I wouldn't even look at the second part. I would say the whole thing diverges. So this integral definitely diverges. Another way to convince yourself of this or think about this is that basically you're adding up something that's infinitely large to something that's finite. And an infinite thing plus a finite thing is still an infinite thing.
So in general, when we are evaluating improper integrals, will it literally be necessary to put the right or left side of the limit?
It is necessary.
Okay, so actual, because I've never seen a problem where it would make it.
Let me show you an example. Let's look at another example. Let's say we want to find, so I should say, it matters in that it's correct. In actual doing of the problem, if you forgot the right or the left hand side, it's not going to make a difference when you plug whatever in to get whatever answer you're getting.
So it's not going to change the answer?
No,
Okay.
But let me show you what I mean by why it matters. Let's say I wanted to find the integral from 0 to 9 of 1 over the square root of x, which is for sure undefined at 0. So I'm going to rewrite this. I keep meaning a number of things. I always fail like not very far into let's see. That could be 3, sure, that could be 4. Numbers are good. 5. So we're going to write this as the limit as a approaches 0 from the right, the integral from a to 9. I'm going to write this as x to the -1/2. And then we're going to integrate the limit a approaches 0 from the right of x to the +1/2 divided by 1/2 from a to 9. And then I'm going to plug in. I'm actually going to write this as 2 square root of x because I prefer to write this as 2 square root of x. I'm going to get the limit as a approaches 0 from the right of 2 root 9 minus 2 root a. And now here's the technical reason why the side is important. The square root of a is not defined if a is negative. So you can't approach 0 from the left because the function doesn't exist left of 0. So that's why it's technically important that we're approaching 0 from the right. But when you actually do the calculation, it doesn't matter if you're thinking of plugging in 0 from the right or from the left. You're still plugging in 0, and you're still just getting 2 times 3 minus 2 times the square root of 0, which is just 6 minus 0. So do you see what I mean by it matters kind of mathematically, but when you actually do the calculation, it doesn't actually end up mattering. That's what I mean by that. So yes, as a math teacher, I would encourage everyone to write the correct side when you're doing it. But as a math student, I'd be like, do what you need to do. I will point out, you never need to specify what side of infinity you're approaching from, because you can only approach infinity from one side, the left side of infinity. There is no right side of infinity. And likewise for negative infinity. Okay, so let's look at some more examples, because there's a few things I want you all to know. Yeah, like this example. Then I want to find the integral from 2 to infinity of 3x squared over the square root of x cubed plus 1. And you might see a pretty straightforward u substitution. If I were doing this problem, I would still start off by noting the improperness first. So I'd be like, okay, it's improper. So I'm going to write this as the limit as b approaches infinity of the integral from 2 to b of 3x squared over the square root of x cubed plus 1. And my personal and professional opinion about this is that I don't want to do a U sub while still writing a limit as b goes to infinity and limits of integration. I don't like that. It's certainly possible, and I will show you how I would do it if I had to do it that way. But here's what I would recommend to do. So here's my recommended route. Do the antiderivative off on the side. Not improper, not definite, just the antiderivative of 3x squared over the square root of x cubed plus 1. My u sub is u equal to x cubed plus 1. My du is exactly what I was hoping it was going to be, 3x squared dx. So this integral becomes the integral of du over the square root of u. Or if you prefer, u to the negative 1/2 du, which integrates as u to the 1/2 over 1/2, or 2 square roots of u, which then, replacing u with x cubed plus 1, is 2 square roots of x cubed plus 1. That's what I would do, because then I can just go back and say, okay, great. Now I know how to find the antiderivative of 3x squared over the square root of x cubed plus 1. And I'm going to get the limit as b goes to infinity of 2 square roots of x cubed plus 1 from 2 to b. And I recommend doing this also, like, really, even if you have just a regular definite integral that's not improper, if you're doing something like with u sub, like if it's an integration by parts and you have to like a lot of pieces, I don't like writing the limits of integration out. I like doing the integral off on the side and then coming back and saying, great, now my definite integral is equal to this nice finished antiderivative with the limits of integration at the end. I feel like that's a more succinct way of doing it. But I will show you another way you can approach this if you wanted to. I don't love it, but I will show it to you. Finishing this off, I'm going to have the limit as b goes to infinity of 2 times the square root of b cubed plus 1 minus 2 times the square root of 2 cubed plus 1. This part here is going to be 2 times 3. But this other part here is going to be 2 times infinity, which is infinity. And infinity minus 6, still infinity, which means the whole thing diverges. Let me point out how you could do this problem the kind of less nice way, in my opinion, just in case you prefer to do it that way. And I'll keep this up here so you can see it, but let me show you. Alternatively, you could do this. So when you get to the limit as b goes to infinity of the integral from 2 to b of 3x squared over the square root of x cubed plus 1 dx, you can let u equal x cubed plus 1, just like we did before, and you can change the limits of integration. If x equals 2, u is going to equal 2 cubed plus 1, which is 9. And if x equals in b, I really don't love it. So not a fan. Then u is going to equal b cubed plus 1. I'm really like so unexcited about this, you wouldn't even believe it. Anyway, we can rewrite this as the limit as b goes to infinity of the integral from 9 to b cubed plus 1 of our du over the square root of u. So what some people do though is they just leave this as b because they justify themselves that if b is going to infinity, then b cubed plus 1 is still going to infinity, which I feel like is a little dicey. So I probably wouldn't do it that way. Yeah, I really don't like it. I know I've said it a few times, I don't like it. Not to my knowledge. Not that I can think of, at least, without going with more thought. Some people might rewrite this as the limit as like c goes to infinity of the integral from 9 to c of du over the square root of u. Basically saying, since this is going to infinity, call it something else. I don't like either of these situations, but either way, you're still going to get divergence, because after you integrate this, you're going to get the limit as b goes to infinity of 2 root u from 9 to b cubed plus 1. I guess the one advantage here is you don't have to change back to x's. But I don't really feel like that's an advantage because we didn't have to deal with that in the other one either. So then if you did it, you get the limit as b goes to infinity of 2 square root of b cubed plus 1 minus 2 square root of 9, and then that's going to be infinity. So diverges. Okay, I don't like it. So if it were up to me, I would always recommend to do your u sub or your integration by parts off to the side, or whatever terrible method of integration you might have to use to anti-differentiate this thing, do the antiderivative, and then go back and plug it in.
One thing that's beneficial to changing the bound is when as b approaches infinity, you get an actual value. So like for arctan,
Sure.
hit 5/4, and that's usually easier to work with because you immediately.
Excuse me, like if you actually do like, but if you're letting u equal arctangent.
Yeah.
Okay, yeah, I don't know if I agree on that, but I can see what you're saying. But the problem is, but the thing is, you're not putting in arctangent to infinity, you're putting in arctangent to b. And then you don't get the pi over 2 until you actually take the limit.
But couldn't you just take the limit and write the limit?
But you have to, you're getting a little hand wavy there.
Okay.
There was something else that I just wanted to mention now. Sorry, I totally went away from me. Oh well, let's do some more examples. Time. Oh yeah, we get time. So if both limits of I know what I was gonna say. No. I was gonna say sometimes with a regular u sub problem, you change limits of integration and both limits end up being the same. That's a time where it's like nice. Like for example, here's a time where it's really nice to change your limits of integration. I know this is not improper. That's okay. Here, if you change your limits of integration, well, what's my u sub, everybody? Right. So if u is 9 minus x squared, and my du is negative 2x dx, or negative 1/2 du equals x dx, then this integral becomes the integral, let's see. So my x dx is negative 1/2 du, and then I have a square root of u. But then if I change my limits of integration, my lower limit is 0, and my upper limit is 0. And so the integral is 0. Now, we also could have seen this was going to be 0 because it's an odd function from negative 3 to 3. But the point I was trying to make was that sometimes when you do a u sub and you change your limits, you get something really easy by just seeing what limits are doing.
Actually, something a little bit nice about doing this a specific type of u sub is, especially with trig subs, often you have a square root under a radical, and doing that you get from the bound that's the same, but you shouldn't actually get that.
Because if it's under the radical, then you have a possibility of being undefined at that point. Not, or obviously under a denominator.
That, but also the possibility that the absolute value changes sign.
Sure, but so it's certainly not an issue here, though.
No, not here. But in general, I know we went over it in the past, but do you think at some point we could go over a little bit about the absolute value again?
Maybe, probably not today though.
Okay.
So let's look at some more examples like this. I've lost my numbers. Oh well, it's good. It's good while it lasted.
This is the sixth one.
All right, no, I definitely wrote down 6 before. We'll call this 7. So what if you have 2 infinities? Well, just like I said before, if you have 2 problems, you have to break it up so that you have 1 problem to deal with at a time. So we're going to rewrite this as the integral from negative infinity to, I'm going to pick 0 of x cubed e to the negative x to the 4th, plus the integral from 0 to infinity of x cubed e to the negative x to the 4th. And here's what I'll say about this. I typically like to deal with each part one at a time. Some people like to write like both limits and then try and do both integrals at the same time. But I'm of the opinion that one of them might diverge. Doesn't happen here. If it can happen, that one of them diverges. Once one of them diverges, you're done. There is a caveat to that statement. If one of them diverges, you're done, unless you're doing a web work problem and they ask in which way it diverges. They might ask, does it diverge to infinity or to negative infinity? And then you have to be more specific. Be like, well, if this one diverges to infinity, then I also need to look at what this one's doing. If this one's finite, then finite plus infinity is infinity. If this one's infinity, then infinity plus infinity is infinity. But if this one diverges to negative infinity, then we don't know how the whole thing diverges. because a negative infinity plus an infinity, if you would just say it diverges and we don't know which way, because infinity plus negative infinity is, oh my gosh, is an indeterminate form. We don't know how we don't know what that adds up to.
There's no way to figure it out.
There is not. And I'm going to show you a really disappointing example in just a minute. Yeah, a real disappointing example. So if we look at this one though, I'm going to do my u sub off to the side. So I'm going to do my integral of x cubed e to the negative x to the fourth. I'm going to let u equal negative x to the fourth. My du is negative 4x cubed dx. So negative 1/4 du is x cubed dx. So this becomes the integral of negative 1/4 e to the u du, which is negative 1/4 e to the u, which is negative 1/4 e to the negative x to the fourth. And we can definitely see that the derivative of that is going to be x cubed e to the negative x to the fourth. So then let's look at these separately. So for A, I'm going to do the limit as A approaches negative infinity of the integral from A to 0 of x cubed e to the negative x to the fourth. And then we know the antiderivative is just negative 1/4 e to the negative x to the fourth. So we're going to get the limit. I should write this up here. The limit as A goes to negative infinity of negative 1/4 e to the negative x to the fourth from A to 0. Plug in the limits. It's too bad that just like how the word sine SIGN and the trig function sine SINE sound the same. It is unfortunate that we have both a limit to infinity and limits of integration. But oh well. So we're going to plug in the limits of integration. So we're going to still have the limit as A approaches negative infinity of negative 1/4 e to the 0 minus negative 1/4 e to the negative a to the fourth. Okay. So as I maybe have said, I don't love negative powers. Specifically, I don't love powers that go to negative infinity. Because I'm never good at being like something to the negative infinity is 0. Like I've gotten better at it over the years, but it took a while. So what I would always encourage, if you can, and usually you can, I'm going to rewrite it in a way so that my power is positive. So if I look at this right now, if I plug in negative infinity for A, I get negative infinity to the fourth power, which is positive infinity, but then it's the negative of that. So it's still negative infinity. Y'all see that?
Wait, when did he, so it's negative A, you put negative.
No, it's negative a to the fourth. The fourth power is happening before the negative is happening. So I would definitely prefer to rewrite this as the limit as A approaches negative infinity of negative 1/4 plus 1/4 times, instead of e to the negative a to the fourth, 1 over e to the a to the fourth. Because now I can see that as a goes to infinity, negative infinity, a to the fourth also goes to positive infinity, and then e to the infinity is infinitely large, and 1 over that is infinitesimally small. So this part here is going to go to 0.
Okay, so if I plugged in A,
Mhm.
would it be a positive power?
It would be, however, here, yes,
Okay, but if it was to like the third.
it would be negative.
Okay.
Yeah. Or you can just get comfortable with saying e to the negative infinity is going to 0. Right? That's also totally fine. You'd be like, oh yeah, I'm going to get negative, right? This part here is going to be e to the negative infinity, e to the negative infinity to the fourth, which is e to the negative infinity, which is 0. I'm just not great with that portion. So then I get negative 1/4. Yeah.
We have negative infinity, let's say because you're saying the difference between the line and the curve is going to infinity, but in the negative side.
Say that one more time.
So when let's say we have some function that approaches negative infinity.
That who diverges to negative infinity? Yeah.
Are we saying the difference between the line and the axis is approaching negative infinity?
We're saying the area between the curve and the axis is infinity, but it's under the x-axis, so it's
So
negative.
it's the difference between the,
Yeah.
okay.
So for part B, we've kind of already done all the work. So what I'm gonna do instead of writing all this is I'm gonna say, well, I'm gonna have the limit as b goes to positive infinity of the integral from 0 to b of x cubed e to the negative x to the fourth. And then I can probably jump to like, I don't know, I can jump a little further for like I know it's gonna be the limit as b goes to infinity of, maybe I can't really jump. I wanted to jump, I don't know if I really can. And then we plug in our limits of integration and you get the limit as b goes to infinity of negative 1/4 e to the negative b to the fourth minus negative 1/4 e to the 0. And then if you're James, you rewrite it. You say, I've got negative 1/4 times 1 over e to the positive b to the fourth plus 1/4. And then just like before, this e to the infinity goes to 0. So you end up with positive 1/4. And then our total answer is negative 1/4 plus 1/4, which is 0. Which is not surprising if you notice that this is an odd function. Okay. Question?
Just have said that.
No, no, no. Let me show you why. I was hoping I was like, come on, man, you give me the question. All right. So here's why we can't say that. Perfectly innocuous looking integral. In fact, we can even draw it. X over x squared plus 1 goes to the point 0, 0. I don't know, you get 1, 1/2, sure. Looks vaguely, I was a better drawer, vaguely like this. And you might think, because of symmetry, that those areas cancel out. And unfortunately, they do not. Here's why. We have to break it up. So I'm going to break it up. This integral is going to equal the integral from negative infinity to 0 of x over x squared plus 1 plus the integral from 0 to infinity of x over x squared plus 1. And I would really, really be super duper excited if all of you knew how to anti-differentiate this without doing a u sub. But it's okay if you need to do a u sub here. The u sub would be u equal to x squared plus 1. My du is 2x dx. So 1/2 du is x dx. So I end up getting the integral of 1/2 du over u, which is just 1/2 natural log of the absolute value of u. Just 1/2 natural log of the absolute value of x squared plus 1. So if I look at my,
Are we breaking it up because it's not defined at 0 or?
nope, it is defined as 0. Right, look at this function. Does that look like it's undefined as 0? Definitely defined as 0.
Yeah,
We're breaking it. Why are we breaking it up though?
we do the A and B for each part.
Sure, but specifically, what about this integral? What about its limits of integration are forcing us to break it up?
They're both problems.
They are both problems, and we can have. And how many problems can we deal with at a time? Just one. So that's why we don't want two problems at the same time. So then let's deal with part B just because it has the positive one. If we look at B, I'm going to write it as the limit as b goes to infinity of the integral from 0 to b of x over x squared plus 1. And that's going to be the limit as b goes to infinity of the natural log of the absolute value, not that I need it, of x squared plus 1 from 0 to b. And I plug in, you get the limit as b goes to infinity of the natural log of the absolute value of b squared plus 1 minus the natural log of the absolute value of 0 squared plus 1. And as b goes to infinity, the natural log of b squared plus 1 goes to infinity. That's going to be 0. So this part is infinitely large. And Once one part diverges, the whole thing diverges. And anyone that tells you different is wrong. I have known of at least one professor who does say that this integral is equal to 0. That is incorrect. That is false information. That is not what is right. Now, I would agree. I would like for this integral to be 0. It certainly feels like it should be 0 because the area to the right and the area to the left seem like they should definitely cancel out. That is not correct.
So I'm having a hard time believing this. Because however I see it, it should be 0, because even if you do U sub, and I mean, couldn't the infinity of the left side be the same infinity?
But do we know they're the same? How would you show that those infinities are the same?
I mean, I imagine there is a way to show that.
Let me double check. What's infinity minus infinity again?
Okay, what if we do the ratio of the two? So,
So I'm gonna catch up. This diverges.
okay.
So that is, and the way you show this diverges is by dealing with one part of it and then getting divergence. Now here's what I'll say. Odd functions, if the integral from negative infinity to infinity converges, then the answer will be 0.
Wait, so is it the natural log of x squared plus 1 or 1/2?
Oh, I forgot the 1/2. I'm
Okay,
sorry.
that's what-
Yeah, apologies about that.
you're good.
Sorry, I got 1/2 of infinity. Still infinity. Yeah, I know. It definitely, when I learned this the first time, it kind of messed me up for a while, but I got over
It
it.
is actually divergent, right?
It is actually divergent.
This class, it is an actual divergent.
Right, no, it's not just here. This is divergent. Like all the time, everywhere. This interval diverges.
On the other side, for A.
Yeah, so if you did it for A, you would get negative.
Okay. So that's where the infinity minus infinity comes.
Right, exactly. But what I'll say generally is typically you don't need to do that. Once if you've done this, you're done.
It's just easier to solve for in this case.
I did B because I had a positive instead of a negative. But you could have used either one. If you'd done A first and gotten to divergence to negative infinity, stop there, the whole thing diverges. And that's really, I would say, overall, kind of one of the important things to know here is that you stop when you know it diverges. If you know a piece diverges, you're done. Well, that thing diverges. We got time, yeah. Let's look at another example. Let's say I wanted to do the integral from -2 to 1 of 1 over x squared. Now, it's really important that you don't just blindly do this one the wrong way. You're welcome. Because if you weren't paying attention, you might accidentally say that this is going to be, well, the integral of 1 over x squared is -1 over x, from -2 to 1, and then you get -1 over 1, minus -1 over -2, which is -1 minus a half, which is -3/2. And that is definitely wrong. Because, well, if you think about it, 1 over x squared is a positive function all the time. So how am I integrating this function that's always above the x-axis and getting a negative number? Well, the answer is because I'm doing something wrong. What I'm doing wrong here is that if I draw this, I can see that this function kind of does this. Oh, I've got a vertical asymptote at 0. So I'm kind of looking at all this area and all this area. But the thing to realize here is I have to break this up at the problem, and the problem is 0. So we have to rewrite this. Integral from -2 to 0 of 1 over x squared plus the integral from 0 to 1 of 1 over x squared. Now let me ask all of you. Generally, when you anti-differentiate x to a power, your new function is just one larger power, right? The integral of x to the -2nd is going to be x to the -1st. Yeah, there's some other stuff there. But the point is that when you anti-differentiate 1 over x squared, you're essentially going to get 1 over x. Meaning, if you're going to get an integral that's 1 over x and you're going to end up plugging in 0, is it gonna diverge or converge?
There.
Right, because you're gonna have one over X and it's gonna be plugging in zero. Whereas, well, in fact, I'll say that in a minute. So if we look at just one piece of this, let's look at, I don't know, let's look at part B. It doesn't really matter which part you look at. Well, that's not true. It does matter. If you have an idea that one part's gonna converge and one part's gonna diverge, it definitely pays to look at the part you think diverges first. But again, that takes experience, I suppose. So looking at part B, we're gonna have the limit as B approaches zero from the, which side of zero are we approaching from? If I'm going from zero, sorry, not zero, from, oh, I did, I used the wrong letter. I used the wrong letter. Like, it's not wrong to do it this way. It feels wrong. Let's call it A. So, am I approaching A from the right side or from the left side? I'm sorry, am I approaching zero from the right side or the left side?
Wait, which one?
I'm doing B.
Oh.
I'm doing B here. So here's section B. And here's section A. So for B, am I approaching zero from the right or from the left?
Right.
From the right, right. And then we get the limit as A approaches zero from the right. We integrate this, we get negative 1 over X from A to 1. We plug in. You get negative 1 over 1 minus negative 1 over A. And then you can see, oh yeah, as A goes to 0, 1 over A is going to blow up to infinity. This thing definitely diverges. Something I've noticed over the years is that when you're integrating something, and because 0 was a problem, because you were dividing by 0, if you still have that variable in the denominator after you've integrated, it's probably going to diverge. Whereas if you look back, if you look back here, just to kind of remind you, in this problem, 0 was a problem. When we anti-differentiated, our X was no longer in the denominator, right? It was X to a positive power in the numerator, and then plugging in 0 wasn't the problem. So you kind of see this thing, whereas if you end up getting out of the denominator, 0 is no longer a problem. On the other hand, infinity would totally be a problem here. Right here, infinity in the denominator is okay, but if you differentiate, if we were going from 0 or 1 to infinity here, that would totally be an issue. So there's patterns you see after a while. I should really do that one with you guys. Cool. Yeah, let's look at. Sure. Here's a fun one to end the day with. Yeah. The integral from 0 to infinity, 1 over x plus 1 times the square root of x. I definitely saw this in someone's homework the other day. It was a good problem. So how many problems do we have? Not nine. We have 2 problems. What are our problems? Obviously, infinity is a problem. What else is a problem? 0. And if this integral was from negative 1 to infinity, which is not, we'd have 3 problems, which you'd have to break up into 3 intervals. So here, I'm going to break this up at any point in between 0 and infinity. I'm going to make the not exciting choice to pick one. Now, I don't have any good intuition about which of these might diverge. And I guess I need to do the antiderivative versus anyway. So let's just off to the side do the antiderivative. Ooh, the antiderivative. Huh. So someone wrote this problem this way on purpose. If I was writing this integral out and was just like giving it to someone, I would have written it as 1 over x to the 3/2 plus x to the 1/2. I would have actually distributed that because it just feels more natural. Someone factored this for a reason. They were trying to give us a clue about what kind of u sub to do. I'm going to let u equal the square root of x, and here's why. I know that letting u equal to the square root of x means I'm gonna get a 1 over the square root of x in my du. Right? The derivative of x to the 1/2 is 1/2 x to the negative 1/2, which I never actually like to write it that way. I really prefer to write this as 1 over 2 root x dx. I find that a much nicer thing to write. But either way is perfectly usable. And then I will point out we have dx over root x in our integral. So I can just get rid of that 2, and I can say 2 du equals 1 over the square root of x times dx. And again, the reason I'm focused on this first is because, as I've said, I can't even count how many times. We always deal with the dx du interchange first. After that, everything's fine, but we have to make sure dx changes to du. So rewriting this integral, I'm going to start by just writing dx over root x is going to become 2 du. And now what am I left with? I mean, I can write it a terrible way. I could write x plus 1, which I really don't like doing, but it's fine.
Wait. So, I'm confused because the square root of x is u, but then
Right?
it's also.
Right. And right. So this is exactly the place where if we'd done things in the wrong order, it would have been an issue. If we had instead decided, well, I'm going to be like, I've got 1 over x plus 1, and then that square root of x is u, then dx, at least if you're doing it like, so, I mean, really, you can do this any way you like. I'm a fan of doing it this way, but I suppose if you wanted to, you could solve for dx and then do that thing. I don't see it that way. But yeah, I'm making sure I deal with this part here changing into du. And then what's left? X plus 1. Well, u is equal to the square root of x, so u squared is equal to x. So this integral becomes the integral of 2 over u squared plus 1. Which is equal to what? What's the integral of 1 over u squared plus 1? Everyone's favorite inverse trig function, arctangent. If we plug back in root x, we get 2 arctangent of root x. Okay, this one turns out to be super cool, I think. So this one actually converges for both pieces. Check this out. This first piece here, I'm gonna do the second piece first. And I do want you all to see this. If you can hang out, you obviously you're welcome to go, but I want you to see this because I think it's worthwhile. So doing this second part first, right? We're getting the limit as b goes to infinity. The integral of this we just found out was 2 arctangent of root x, right? I don't want to write all this again. In fact, not only do I not want to, the whole reason doing it over here was I didn't write it again. From 1 to b, and then we do the limit. B goes to infinity of 2 arctangent of the square root of b minus 2 arctangent of the square root of 1. Okay, as b goes to infinity, the square root of b goes to infinity, and the arctangent of something infinitely large is right. That limit comes up kind of often, especially in these improper integrals. So you're gonna get 2 times pi over 2, and then what's the arctangent of 1? Ooh, right. Yeah. So we end up with pi minus pi over 2, which is pi over 2. And then for the other one, for part A, same deal. We're going to do the limit as a approaches 0 from the right, I guess, of the integral from a to 1 of 1 over x plus 1 root x. So here's what I point out. If I wanted to skip a step, the step I would skip would be, I'm going to write this as the limit as a goes to 0 from the right. I know the integral is the arctangent of root x, and I'm going to plug in the top and then plug in the bottom. So I'm going to get the arctangent of the square root of 1 minus the arctangent of the square root of 0. Sorry, square root of a. And just like before, arctangent of 1 is pi over 4. I forgot the 2. Sorry, terrible human being. 2 times pi over 4 minus the arctangent of 0 is 0. So I end up getting 2 times pi over 4, which is pi over 2. Then we add them together and we get pi over 2 plus pi over 2, which is pi. So this integral converges to pi. Kind of neat. All right, that's all. That's not all, but that's all I have to say for today about improper integrals. Just make sure that you're only dealing with one problem at a time. If your integral has 2 or more problems, you have to break it up into multiple intervals. You are welcome. Yeah. Yes, exactly. Good point. If one of the pieces converges, we're not done. We have to check the other piece. The other piece might also converge, which means the whole thing converges. It diverges. Right. And that's why I said before, if you have any sort of intuition about which might be the one that diverges, it's good to try and do that first. An example of this would be, take 1 second here. Yeah, this integral. So I will just point out that you can break this up into the integral from -infinity to 0 of x squared e to the negative x cubed, plus the integral from 0 to infinity of x squared e to the negative x cubed. Now here's what I would say, and I'll leave you with this. I would do this one first, and here's why. If you plug in negative infinity for x, what's negative infinity cubed? Still negative, but then the negative of that is positive infinity, right? So the idea that what I'm seeing here is that this is essentially an e to the positive infinity over here, which means it's very likely that this section diverges. This probably, I'm almost sure, diverges. On the other hand, over here, if I plug in infinity, infinity cubed is infinity, and negative infinity, e to the negative infinity goes to 0. So this one probably converges.